Last time out I discussed pen faults and how they relate to EV charging. That raised a lot of discussion in the comments regarding the fault itself, the likelihood of the fault occurring, and how you might avoid the risk it poses. In this video I want to follow up on that previous one, clearing up some misunderstandings that became apparent from the comments, including a couple of small mistakes I made in what I said, so that we're all on the same page. I'll also cover the alternative approach to my recommendation from last time. In other words, how you can continue to use a granny cable if you so desire, but do so most safely. Hello everyone, I'm Andrew. Thanks for joining me on the electric transition. As I mentioned in the intro, I had a lot of comments on the last video from lots of different types of people. Somewhat unexpectedly, getting comments has turned out to be one of the best bits of creating videos. As well as getting the opportunity to understand how other people feel about the subjects I cover, I also get to learn from other knowledgeable people who might clarify things I didn't know, or sometimes get to understand that I didn't explain them very well. And so it was this time around. There were some great comments last time out, with lots of detailed information for those who managed to read them. Thanks to everyone who comments on videos. I really appreciate you getting involved with the discussion. I like the community feel we've got building up, so check out the comments after a video launches if you can spare the time. As you may have gathered, this video builds on the last, so I'll link to that last one from the end screen as well as from the description. You might want to watch that for a more detailed understanding of this topic if you haven't already done so. Okay, this time I want to start by saying that charging electric cars has proven to be extremely safe. I didn't mention that last time out, but they do a bunch of safety checks as part of the charging start process, and we've not heard of issues. I mentioned the concern with pen faults because it's an unusual type of fault. This is not an issue with the car, of course. Instead, it's an issue with the way that homes are being wired. As someone mentioned in the comments, there is also a risk from using outdoor appliances in the event of a pen fault. Lawnmowers, trimmers and hedge cutters are mostly plastic these days, partially because that makes them cheaper to make. However, it also makes them safer, and that reduces the risk that the manufacturer gets caught up in legal action should anything go wrong. Double insulated tools are just less risk for them from the legal perspective. Having said that, a couple of people mentioned electric log splitters and asked would they be a risk too. The answer to which is yes, definitely. They are going to need to be very strong, which results in them being made of metal. Hot tubs came up in the conversation too, and yes, you'll have to be very careful with those. Water and electricity together are a risk, but in a pen fault they are a terrible mix, just because the flow of electricity through you could be greater if your skin is wet. In a way, fixing the car is just a partial solution to minimising the risk from pen faults. Having said that, it might be true to say that you use your car very regularly, so it makes some sense that we give it more consideration in this respect. The next point that was discussed at some length was the frequency of occurrence. How often would this really be a risk? Fortunately, I found a bit of data about that. A story published by Engineering and Technology in November 2022 included data obtained from a Freedom of Information request. That data showed there to have been 474 pen faults reported in 2021. That's the number of faults reported, but it's thought that some faults might not be reported, so the true number is probably a bit higher. Furthermore, each fault could affect multiple properties. Finally, the charity Electrical Safety First has reportedly said that about 10% of pen faults result in injury. That suggests there were something like 40 to 50 injuries in that year. However, I have not been able to verify that information online. I think we need some context though. For reference, there are about 130,000 injuries on the UK's roads each year, about 30,000 of which are considered serious. This helps put the risk from pen faults into some context. This is rare, despite being non-zero. Even so, there can be a difference in the protection we are provided from them based on the charging method we choose. A dedicated level 2 charge point installed in the UK must offer protection against pen faults in some way, whereas a level 1 or granny cable need not. Someone in the comments said that they thought every granny charger probably had protection, but I can confirm categorically that they do not. My granny cable is by Masterplug, or at least it has the Masterplug logo on it. These days Masterplug are owned by Luseco, whose kit I do not really rate after having some LED bulbs of theirs fail almost instantly. I went looking for the specifications of my cable to see if it said anything about pen faults, but unhelpfully the online listings simply refer you to the packaging, which I don't have as I got mine second hand. I went to a shop to see if I could get a look at the packaging, but sadly, despite being able to order them from that shop for collection in store, they don't have any in any of the stores. So I decided to check myself. I opened it up and had a look. Now I've got to tell you not to try this at home, of course. Do as I say, not as I do. The first clue is from a look at the components on the circuit board. We can see that there are two relays, those two dark grey things in the centre of the board. That's not enough for pen fault protection. But to be sure, I lifted the board out and looked at the back. On the front we can see that the earth conductors attach to screw terminals on the same side of the board, roughly in line with one another. Flip it over and on the back we see those two terminals here and here, and they are directly connected by a track on the PCB. So from that examination we know that this doesn't have pen fault protection. You see, there's a weird thing about pen faults. What we learn when we study electrical systems is that the protective earth conductor, officially called the CPC, should always be unbroken. It's there for safety and should always remain intact. It shouldn't go through breakers or switches. It has to remain attached at all times, except in the case of a pen fault. The peculiarity of this fault condition is that we have to go against our instincts. In this fault scenario, it's the CPC itself that carries the risk. It is what could expose us to dangerous voltages. Let's have a look back at the logical wiring diagram we showed last time out. This is a simple representation of an electrical installation showing an incoming electrical supply feeding a resistive heater. We see in the diagram that there is an electrical circuit from live through our appliance back along the neutral wire as normal. In this TNCS system, the neutral inside of the property connects with the CPC at the entry to the property, often in the meter box. That's what's unusual about the wiring of a TNCS system. As our heater has a metal case, we've connected that case to the CPC. We consider that to be a safe thing to do because the CPC should be at the same voltage as the ground on which we stand, the literal planet Earth. Now let's change the diagram to show our fault condition, where the pen, the combined protective earth and neutral wire, is broken just outside of the home. At this point, in the simple circuit I've represented, the heater no longer works. There is nowhere for the current to return. It can't go back to the source along the neutral wire to the local substation. Therefore, no current flows. The heater is off. However, if we now attach a person to the metal case, we have a new circuit. The new current path is along the live through the heater's resistive element back along the neutral wire to that bond to the CPC, then along the CPC and through our person, who might be standing on the earth in a lean-to in which the heater is situated, unaware of the risk. This circuit can be simplified as a 27 ohm resistor, which is what the resistance of a 2 kilowatt heater element would be, and our person, who might be a few thousand ohms. The voltage of the supply is split across the two in the ratio of the resistances, and so the person gets the majority of the supply voltage across them, about 227 volts in fact, which is well above the 50 volts AC considered potentially dangerous. If we replace our heater with an EV, the problem is exactly the same. In the event of a pen fault that matches this particular scenario, we're still going to get a nasty shock by touching the bodywork of the car. The only way we can avoid this risk in the case of a pen fault is to break the CPC. If the CPC isn't conducting, then the metalwork isn't attached to the faulty system in any way, and our person will be safe. And that's exactly how a pen fault protector overcomes the dangerous situation. Unusually, it breaks all three conductors. It breaks the live and the neutral, and also the CPC. It's the only type of protection allowed to break the CPC. This is how we know that my granny cable does not offer pen protection, because there is nothing in it that breaks the CPC, which is a requirement for this sort of protection. At this point, I want to address another question from the comments, which was whether other protection mechanisms can save us from this fault. Firstly, RCDs, known as GFCIs in North America. I used to refer to these as earth leakage circuit breakers, which is a nicer name in my opinion. However, it leads to confusion as there are two types of ELCBs. What RCDs and GFCIs sound like they do is measure current flowing in the CPC, the protective earth conductor. However, they do not do that. What they actually do is monitor for a difference between the current flowing out along the live wire and back along the neutral wire. If the two currents are different, that suggests there is a leak somewhere, presumably to earth, and so that imbalance is what triggers them. Unfortunately, in a pen fault, the current path is out along the live and back along the neutral before then running along the CPC. It's this unusual current path that means RCDs and GFCIs do not trip. The current on live and neutral is perfectly balanced, so they see no fault condition and can't help us. Other people asked if surge protectors or SPDs help in this situation. They are intended to clamp short, transient spikes in the incoming waveform, and that's not what our fault is, so they don't help either. No, it's only pen fault protectors that can help in this scenario, which, as it happens, they do by measuring for unusually high or low voltage differences between live and neutral. Low voltage being a trigger makes sense. In the simple fault condition we talked about, the neutral isn't connected to anything directly, so the voltage difference between live and neutral is nothing, and remains almost nothing during the fault, even when the person is attached. High voltage conditions, on the other hand, are a bit more difficult to explain, so I'm not going to try in this video. However, the description contains links to John Ward's videos where he explains it. His series of 3 videos on diverted neutral current touch on that, if you want that level of detail. It's a bit of an eye-opener when you understand how a pen fault could expose all of the equipment in your home to 400 volts in the extreme. Eek. Anyway, let's get back to those comments. So I think we've disproven the idea that all granny cables probably contain pen fault protection. Mine doesn't for sure. We saw that when we looked inside. In fact, I'm not sure that many will. These things are made to a price, and there is no requirement for them to offer this additional protection, so often they probably don't. However, what came as a nice surprise from the comments was that some do. The latest Masterplug granny cable, which superseded the one I have, does contain the appropriate protection. It says so in the marketing blurb. What's more, the Tektron EVP3 also offers it. That's not a brand I've heard of, but again in the marketing blurb it says it offers both RCD and pen protection. This is not an endorsement of that product, as I really know nothing about it, but the point is that some granny cables do offer pen fault protection, but not all of them. Therefore, if you want to keep using a granny cable and you would prefer to avoid the risk of pen faults, then you could ensure that you have a granny cable with protection. That's one way to sidestep the problem. However, the other thing you could consider is protecting the circuit into which you plug the cable. As we discussed earlier, your car is not the only thing that exposes you to risk. Any metal electrical appliance used outdoors might. If the circuit you intend to charge from is also the circuit you intend to power tools from, then maybe protecting that whole circuit is an option. A commenter mentioned that their charging circuit includes a MAT-E device. That's a British company, again one I'd not heard of, but they offer pen fault protectors for hardwiring into your circuits. It would be good to support a company designing and building devices in the UK, so consider that if you want a permanent solution, but there are others on the market too. I'm sure an electrician will be able to recommend something if you want that. It depends on the layout of your home as to whether that works, of course. These are not intended to protect a ring main, but a spur. However, if it works for you, that's a solution that fixes not just your EV charging. So there's one last subject to cover that appeared in the comments, and that's whether the diagram I showed was too simplistic. After all, a number of people said, you have an additional earth connection through your water and gas pipes. To which the answer is maybe. We don't actually apply an earth strap to metal pipework as an extra earth as such. Instead, it's intended to ensure equipotential. That is to say that everything highly conductive is at the same voltage. Hopefully that will be 0 volts. It will be a true earth potential, but that's not guaranteed. It used to be the case that gas and water pipes were used for earthing of properties in the UK, but this practice was outlawed in the 14th edition of the wiring regulations, introduced here in 1966. The reason for the practice being discontinued is that this is increasingly less likely to work. Even back in the 60s, it was recognised that repairs to the external mains systems might be done with plastic pipework. And that is ever more the case. In 2002, the UK's Health and Safety Executive introduced a mandate called the Iron Main Risk Reduction Programme, or IMRRP. This mandate required all iron gas mains within 30 metres of a building to be replaced with plastic pipes. Well, almost all of them anyway. You might have noticed this work ongoing ever since, and it's scheduled for completion in 2032. New builds are likely to have had plastic gas pipes since the mid-90s or so. Before that, even if the supply pipe in the home is metal, it's not all that likely to be connected to a metal main in the street anymore. The same has been happening to some extent with the water system. Up until the late 1960s, water pipes into homes were made of lead, until using lead was banned at the end of the 60s due to concern over the lead contamination of the water supply. During the 70s and 80s, water supplies were instead copper or galvanised steel, before they too switched to plastic pipes in the mid-90s or so. What's more, the recommendation these days is to replace any remaining lead water pipes. However, the homeowner is responsible for the pipes on their property, and so this isn't something getting done by decree, as it costs the homeowner money. Note too that some water companies are slowly replacing their iron water mains with plastic ones. They use prediction algorithms to determine areas of their network at risk of bursts and then proactively replace them when they can. As a result of these changes, some houses will have earth continuity through either their gas or water mains, and if that continuity continues far enough, you might get a good low resistance earth from those pipes. Newer homes, anything built since the late 90s or so, are unlikely to have either, as they will have plastic pipes to their homes. However, a bunch of homes will have a mix of metal and plastic along their supplies, and so the resistance of the electrical path along those pipes won't be very good. They may still conduct, but they won't conduct well. In those cases, the load and the earth return path will form a potential divider. On the inputs to the circuit should be 230 volts or so in general, and the final connection to neutral back at the substation will be 0 volts. If you remember, our 2 kilowatt heater has a resistance of 27 ohms, and the resistance of the earth return is the other part of the potential divider. The voltage on the metalwork in the home is determined from the ratio of one resistance to the other. If that earth resistance is just 10 ohms, which it could easily be if not more, then the voltage on the metal case of our heater is 10/37ths of 230 volts, which would be just over 60 volts, more than the 50 volts AC considered potentially dangerous. For context, an earth rod, something designed to provide a reasonably low resistance earth path, is expected to provide an earth with a resistance of about 20 ohms, twice what we said our pipes might provide. The problem here is that high power devices like electric heaters, or our EVs for that matter, offer a low load resistance. In these scenarios where the load and the return earth path form a potential divider caused by the earth return resistance being greater than 0, we are at risk of being exposed to dangerous voltages in the event of a pen fault. Alright, so let's summarise what we've talked about today. First, I pointed out just how safe EV charging has proven to be. The cars do a whole host of safety checks before initiating charging, ensuring we don't have major risks. However, the wiring of some homes can theoretically let that down. A pen fault is not a problem with the car, but a problem with the supply, and any metal object could pose us a risk if this type of fault were to occur. We put some figures on the number of reported pen faults occurring in the UK, which was 474 in 2021, and it's thought that about 10% of pen faults result in injury, although I don't have a confirmed source for that statistic. That's not a very large number though, and it's about 2 orders of magnitude lower than the number of serious injuries on the UK's roads each year. The likelihood of occurrence is quite low, but it does happen occasionally. Next, we discussed whether other protection devices we have, RCDs, GFCIs and surge protectors, would help in this scenario, and unfortunately none of those can help against pen faults. Then we discussed whether bonds to gas or water pipes might avoid the risk, and the answer to that is maybe. In some homes you might have a low resistance earth as a result of those bonds, but these days it's far from guaranteed. In a number of other cases you might get an OK earth of 10 ohms or so, but because our EVs offer a low resistance, or impedance in technical terms, an earth of just 10 ohms is too high to protect us from injury. However, there are a few things we can do to further reduce the risk from pen faults when it comes to EV charging. We could use a dedicated EV charge point. In the UK, that has to be installed with protection of some form. Alternatively, we could have an electrician install a pen fault protector on the circuit we use for charging with a granny cable. That might protect not just the car, but also any garden tools, if that's where you plug them in. However, the easiest DIY solution, if you want one, is to make sure the granny cable you use has protection built in. Some do, but as I showed, not all of them. Maybe do your research about the one you have if that's what you use. If it has protection, then it should say so somewhere. If it doesn't say so, then it's probably safest to assume it doesn't. I have to say, I'm not a fan of the TNCS wiring system. When I am elected supreme leader of the world, I shall start a consultation on whether we continue to use it or whether we instead ban it. The reason for using TNCS seems to be to reduce the cost of the network, but in the modern world, when everyone is moving to EVs and heat pumps, rather than reducing cost, it seems simply to move it to the consumer. In the meantime, while I remain simply a creator, we'll have to be aware of pen faults and consider whether to incorporate some protection against them as part of our charging solution. Hopefully, as a result of these two videos, you are now better informed and have the understanding on which to base that decision. Thanks very much to those people who showed their support for the last video by using the Buy Me a Coffee link in the video description. That's much appreciated, and the link is there again for anyone else who would like to do so. Right, over to you then. I look forward to your comments and questions on this latest video in the comments section. Tell me, do you feel that you now better understand the risk of pen faults? Do you have the information you need to help make a decision on how you charge? Have I changed your mind about your choice of regular charging method? Let me have it in the comments section. If you've liked the video, then it's a big help to me if you click the thumbs up button. And I'd love to have you as a subscriber of the channel if you want to see more from me. Subscribing is free and helps ensure you know about any future videos I make. Thanks.